Well, welcome to week 6, and we're going to continue talking about accounting and water resources. There's sort of three themes that go through what we're talking about today. First is that civilizations have been defined by their large water projects. And sometimes these water projects become so large and complex that it makes the civilization unstable. The other is that we're going to explore some appropriate technology, green infrastructure, and small projects that may actually be crucial in defining our sustainable future. And the third theme is that when we're making decisions about environmental projects, we really need the right indicators. We need to have the right information at our fingertips so we can say whether we're improving the ecology, the economy, and society. So the topics for this week is I'm going to split this into three sub-lectures as I did last week. And in the first part, we're going to talk about water resources, large projects, gray versus green, ecosystem restoration, and then accounting for ecosystem services. In the second part, I'm going to talk about smaller scale projects, what we call appropriate scale, because they're targeted at a very specific project and use very adaptable technology. We're going to look at water pumping, water purification, and then some of the risks. And one of the risks is when you're trying to provide your own water on a small scale, you really have to deal with the risk of drought. And then the final set of slides, it's going to be about measuring improvement, and this will be going back to accounting and indexes. What do we want to measure? What is an index relative to the data and the reports? And then what are some environmental indexes we might consider? And then we're going to focus on the genuine progress index. So, large water projects have held civilizations together. The Aztecs had a series of canals and used the water release into these canals to create food to feed a very large population. The Mayan civilization had much better access overall to water, but still there was water storage and water access issues. And the Anasazi in New Mexico, they had the water system that brought in waters from the foothills into the irrigated agriculture areas, and they had an enormous civilization there with very large buildings and centralized civilization. But this same large water project may have been sort of a seed for their collapse, because as they had to have more and more water supplied to the central area, they needed more and more canals, which required more and more taxes, and it was just spiraled out of control because of the size and the complexity. Their current day large water projects that serve many purposes, and you're probably aware of these, but I want to remind you of them. So we have, in the United States, we have some large dams that they create reservoirs. They produce hydroelectricity. They're used for transportation and flood control. And those are Tennessee Valley Authority, Columbia Basin. These are huge projects that cover many states, and they are run by the federal government and represent a main contribution to the electrification and industrialization of these parts of the United States that they serve. There's also aqueducts. These are just for moving water around. And if we look at the California aqueduct system, you can see that it's a series of canals that move water all around the state, and that moves an enormous amount of water. And if we look at California in particular, there's the aqueduct, which I think maybe everybody's heard of because it's such a prominent feature of of the water literature, and it serves from the Colorado River, moves this Colorado River aqueduct, moves water over to LA, but also moves water up into the Central Valley for agriculture. But there's also a lesser appreciated set of canals up here in Trinity and Shasta that move water between rivers and reservoirs and actually sort of move the water. They pump it uphill for part of the year and store it. And when there is water, which right now it's a sort of a major drought issue, but forms a large water reservoir that's used to support agriculture in the northern Sacramento Valley. So these, if you just look at all the water projects up and down California, this is a major activity moving water around. And where there's water, there's agriculture, and where there's agriculture, there's food production and jobs. So this has a major impact on the agricultural output and economy of California. In China, they're undertaking a very large project to divert water from the south, where there's generally more rain and water availability, to the drier north. And the water, these tiny little dotted lines are the canals that they're putting, and you can see they connect from the Yangtze River up north toward Beijing, and from the Yellow River, using the rivers as part of the system, but moving water all around. And this huge water diversion project will be the largest in the world, even more so than the California aqueducts. So right now they're creating these channels. They've created the dams. It's a huge project to move water around, and again in support of to support agriculture. They're not moving all this water just for drinking water. They're moving it to support agriculture. So those are a couple of types of systems that we're familiar with: dams and reservoirs, these aqueducts. But then there's also large water projects, such as in Florida, the Everglades. It's a major construction project to create the levees and the channels that move water around in the Everglades. And the attempt is to recreate a healthy wetland in the Everglades, to have water move from north through south through this big sea of grass, and try to have the water move in a more natural way to preserve that ecosystem and provide pure water. The story of the Everglades is a very interesting story if you ever get a chance to follow up on it, how every 20 or 30 years there's a reversal in policy and a change in how they manage it, and it ends up being a large ongoing project. I want to just compare drinking water supply as one example of large water projects. So this would be drinking and domestic water supply, really. We think of it as drinking water, but people only drink a very small amount of water. They use mostly for showers and washing and flushing the toilet. That far exceeds how much water we drink. However, when you're exposed to this water, it's important to remember that when you drink water, it goes right into your stomach, which is very used to handling insults from large numbers of different types of inputs. When you take a shower, you're getting water just aspirated right into your lungs, and that's a major... so you don't want to take a shower in water that's contaminated with microbes, because that's a direct route right into your lungs. It's a source of disease transmission. In Portland, we have the Bull Run watershed, a large watershed that's on the east slope of the west slope of the Cascade Mountains and near Mount Hood, and catches a lot of rain and fog and snow, and it's just a naturally excellent place to put a watershed catchment. It's protected. People aren't allowed in there. There's very limited use. It allows for clean water to be collected in this watershed. Portland also has a series of wells that they can pump groundwater when the water is low, and this was one of the questions. If you look at the crux question from week 5 and the response, my feedback. One of the students gave an excellent response about how here you've got surface water coming from rain and snow, and then when the drought gets down, you've got pumping, and so you need to know what's the amount in each of those to be able to trade it back and forth. Los Angeles has a system of groundwater and water reservoirs, and also transfers, as you saw from the aqueduct. Again, thinking of it as drinking water is misleading. Most of that water that they use from the aqueduct is for agriculture, and the other water that comes to LA for drinking water is often brought in from municipal water sources. And New York City reestablished a whole watershed up just north of the city, west of the city, to provide water for their city's purposes. And they did that by reducing pollution in that watershed from dairies and other sources, and then reestablishing forests. And so they have this enormous watershed that supplies their water through clean water through sort of natural processes, sort of like Bull Run. So the environmental impact of these projects is enormous. We're just talking about these large water projects now, and that's because if you look at the impact equal population affluence technology relationship, these projects are large and essentially irreversible. Once you dam up a river, once you create aqueducts and start diverting water, once you establish a whole watershed with pipes and pumping stations, those are large projects. And then again, given the population that these projects I've just mentioned serve, California Aqueduct serves up, a state with an enormous economy, the affluence, all of the consumption and the economic factors that depend on this, and then again, the technology is locked in for these purposes, except for maybe like Bull Run watershed or New York City watershed, but still there's a huge system of pipes and pumping stations that is essentially irreversible. So one way to think about changing this is to go from, instead of large dams and concrete projects, but to try to use more green infrastructure. So gray infrastructure is engineering that might use a lot of concrete and steel. Green infrastructure is that the projects depend on the plants or the ecosystem processes. We're going to talk in just a second. We'll be talking about accounting for ecosystem services. I just want to give an example of how you might cool water, either using a cooling tower or wetlands. So we have the heat load in Oregon. The heat load into streams is one of the biggest pollution problems in the state, because all the water we use domestically as we release it from our homes and from factories and from other uses of water, as it flows back into the streams, it's warmer. So we could use cooling towers or other engineering technologies, chillers, to treat the water for domestic, to cool it down. And there's a picture of a large cooling tower we might use for a nuclear plant, but it's the same idea. These cooling towers are large structure, and by just having air flow in and go across wet surfaces, there's evaporation, and then that cools the rest of the water. So some water is lost into the air as evaporation, but that cools the rest of the water. Little stripe through here just because for two reasons. One, I don't like this, and the other is I don't have the correct attribution for this figure right now, and that's going to remind me to fix it. Alternatively, like we saw, if you took 101, or if you know about this in Albany, they have the talking water gardens, and they turned, instead of using a cooling tower, they used a series of ponds with natural flow between them, some pumping, and a lot of vegetation, and this cools the water down so that when it flows back into the Willamette River, it's cool to the temperature that they need it for the fish and other organisms in the river. Now I want to make a comparison between these two approaches, because we might love, for environmental scientists like myself, we love this sort of thing. There's birds and fish and frogs and everything here. This is just some ugly thing on the landscape. So if we do a comparison though, a realistic comparison. Let's be pragmatic about it. Cooling towers are known technology, and they've been employed and tested. They know how they work. They can manage them. You can have a few people there say, okay, well, let's run it. We're going to cool the water down. Wetlands are more experimental. May take a lot of tweaking to get it to run right. You have to pay biologists, and sometimes they just don't quite understand the engineering mindset that we need cooler water coming out. So there's a problem with that for management. Wetlands have other anticipated issues such as diseases, the spread of having ponds around leads to mosquitoes, which can transmit diseases. Another good thing about cooling towers is that the factors that lead to cooling tower failure or underperformance are not related to ecosystem stresses. So relatively unrelated compared to if you're trying to protect the ecosystem in the river by using another ecosystem, it's likely that there's a connection between those two just in overall performance, and the underperformance of a wetland might lead to more stress on the river ecosystem. So those are more likely to be tied than, say, an engineering structure. So you could have the wetlands fail because of ecological or biological reasons, and that would also have repercussions for the natural ecosystems you're trying to protect. Cooling towers are basically ugly. I don't think anybody thinks these are really a nice thing to see. Wetlands can be beautiful, but you're only going to see them if you're right there. So, you have to actually go and visit a wetland. It's often hard to even see that there's a wetland when you're driving by on the highway because they're flat. It's not like you're creating some sort of large structure. And one of the underlying reasons is if you're a business, you can be fined if your output from your factory or whatever is has too much pollution or is too warm and putting it into the stream. But there's no real, so you want to make sure it works. There's no economic benefit for you. There's no payback if you provide something that looks good and provides recreational amenities. You don't get paid for that. You just get fined in the other case. So the system of incentives is pretty strongly favors using best management practices, which would indicate doing something like a well-tested engineering solution. Another example that we're going to see later is watersheds versus engineered treatment and storage, and that's simply store the water and have water being supplied all year through a well-managed forested watershed rather than creating a reservoir or some big tank. Okay, I want to talk about this in terms of, again, large projects, but we're going to be talking about using healthy forested watersheds to deliver more water. So the way it works is that the leaves of the tree intercept the rain, the plants cover the soil, you don't get as much erosion, the surface and the surface soil and the organics in the soil act as a sponge and they hold the water. The roots break up the soil to create passages for percolation of water into the groundwater. And the combination of all these sort of beneficial things of plants, even though it means that there's, in many cases, there's an observed positive feedback between loss of ecosystem and loss of overall water. And in the Amazon, this is very stark. A vegetated system has a lot of trees that lose water into the atmosphere, and it actually absorbs more of the sun's light directly, but the water cycles through there. The humidity goes back up to the atmosphere and then rains down, goes up, rains down. So you get this cycling of water. Whereas in a deforested watershed, you have less loss from evaporation transmission. You have more reflection, so you think it's like a lower energy budget. But what you do have is just less humidity, and that humidity there never reaches a critical point where it rains back, and that is just taken out of the landscape. So in the vegetated cycle, you keep the water in the ecosystem. In the deforested, you lose that water out to other parts of the country, of the landscape. So this is generally what we're talking about with a forested watershed. You get, by having trees that provide all these benefits, you actually have more water available for humans to use coming out of a forested ecosystem. So restoring damaged forests or reforesting places is one of the ways that we can have watersheds produce water for us. And the Nature Conservancy model is, you can follow this later by clicking on this. The Nature Conservancy model is that they're going to have the watershed create water for cities, and then somebody's going to set up a water trust, and this is where the Nature Conservancy and their financial activities comes in. The water trust manages the forest and sells the water to the city. So the first example of this on a large scale was Quito, and in Quito, the 2 million people, 80% of the water comes from a forested watershed that the Nature Conservancy helped set up. It's run by a local organization, of course, and every year $1 million comes from Quito to help maintain and establish more forested watershed. So this is a way where this is a financial mechanism by which they could take the provision of fresh water to the city of Quito and turn that into a mechanism to create a trust and save this water. We're going to come back to this article on the Niger, and last week you saw this video on the green belt where having more trees led to more water, and it wasn't just one thing. It was water, jobs, agriculture. Okay, now there's some other examples of these projects, and I'm just going to talk about them real quickly, and you're going to come back to them. There's a really nice video about rainwater harvesting in India, and one of the things is that there's by paying attention to restoring the ecosystem, you can actually get more water. So in India, they have these small catchment dams, very, very small for a local community, called a johad, and those were taken out and they were misused, and the trees were cut from around the sides of them and everything like that. So what they started doing is putting those back in, and by putting those back in, it was the opposite of the tragedy of the commons. What they got is a reservoir of stock watering for those that put these little catchment dams back in. But as the trees grew up around the side, there was fish in there. There was a whole bunch of other benefits, and then over time, it built a community resource by recharging the groundwater, by providing fish, and providing these other ecosystem amenities. There's also a couple examples here from Green Empowerment, and Green Empowerment is an NGO located in Portland, but does their work all around the world. And one of the things they focus on is using renewable energy to create resources for local communities. And the couple examples that I show you here is one is where they set up a microhydro, like water coming down a very steep stream. They put in a little electrical generation facility. They use that to create jobs, and then they also used it to fund the protecting that watershed. So they had the watershed for water and energy uses, and by funding that, became a sustainable resource. Okay, there's several examples here that are very useful, but they all illustrate the same same point that I'm trying to make on this page, is that healthy forested watersheds can deliver water as an alternative. So let's look. We're going to come back to that a little bit when in the next video segment when I talk about smaller scale. Let's look at the final thing was, well, how would we account for all of these different services? We said, well, here we get water out of the ecosystem, but we also get a lot more benefits from a forested ecosystem. And in order to do that, we need to account for ecosystem services. So the main services we get from an ecosystem are the provisioning, such as water, that's what I mentioned before, also clean air and soil and plants for agriculture. the ecosystems provide regulatory functions, such as they regulate water flow over the year, they regulate climate, temperature, and rainfall, as we saw. And then there's also cultural and sort of recreation and aesthetic values. So if you just say, well, we just want the water, and that's what they did in Quito, they were able to generate $1 million from that one forested ecosystem. But what's the actual value of that ecosystem services that came from that forest? Well, Costanza and a lot of other authors wrote a really seminal paper in 1997, and that team looked at 17 ecosystem services and 16 biomes, 16 different types of vegetation, soil, and climate across the world. And they worked on published values and calculations, and they also had to calculate a lot of these things, sort of make estimates for themselves. And all of these things were outside of current economic calculations. So it wasn't water being sold by a profit company. It was just like water provisioning. And the range of ecosystem services that they estimated was between $16 and $54 trillion per year, with an average of $33 trillion per year. And just to put that in context, the world's gross national product is $18 trillion. So it was about twice the average. I mean, the average was about twice the formal economy. So here's the method they used. So first of all, they didn't just calculate it from zero, because at zero natural capital there'd be zero human welfare, and this was partly an economic statement and partly a philosophical statement. What they did is most of them depended on sort of a marginal value approach. Like if you had a certain amount of forest and you added more or took it away, what would be the change per that area, and then use that to calculate the total value. So if we look at the biomes, they looked at 16 major biomes, and some of those are lumped into open ocean. I'm just giving you an example here how these calculations would be made. So they had several areas in the open ocean, and there's 33 million hectares in the world of open ocean. And then they put in these values here, like what's the dollar value for gas regulation? What's the dollar value for climate regulation that comes based on the efficiency of the open ocean to regulate gas? So these values go in here, and the references at the bottom of this page, and you can look up this table. It's really a large table if you have 16 biomes and 17 ecosystem services. I'm only just showing you 4 biomes and 3 of them, and just for the purposes of how they calculated it. Then you sum up overall the different values per hectare, and then you multiply the total value per hectare for all of these functions by the total area, and you get this total value of ecosystem services provided by the open ocean per year. And it was 8,381 times $1 billion. So this was $8 trillion just coming from the open ocean. And you go down the list, the coastal, terrestrial, wetlands, each of these major categories of biomes contributed, and the final total was again $33,000 billion, or $33 trillion. So this is where they got that number from, this very large table, and the real work was calculating what were these value functions per hectare. Okay, that's a very interesting approach, and what it shows for a lot of areas is that the value of a forest is way more than you would calculate if you just said, well, how much water are we getting out of it? It does all these other ecosystem services. I'm going to show you an example here in just a second, 2 examples. One of the problems with this is that it's not equal distribution of those ecosystems across the world. So there's areas with very low ecosystem service values and areas with very high ecosystem service values. So again, look at this plot here. The colors are 100, 1,000, and 10,000 US dollars per hectare per year. And these red areas are areas where they're probably marshes or lakes that have a very productive fishery, or they're coastal zones. The green areas, like we see in the Willamette Valley, these are in the range of several $100s per hectare per year of ecosystem services, just for all these other things they produce, not the direct use of that land. And you look at the Amazon, the whole Amazon area is up in this over somewhere in this several $1,000s per hectare. Okay, so that's one of the problems, is that it's not evenly distributed. So there's areas that are going to be rich in ecosystem services and areas that are poor in ecosystem services. Okay, so I have two examples of how we can use that ecosystem services. One is very close to home. One is this idea of in Portland. There's an area of Portland, because of Johnson Creek, has always had a flood problem, and the project that they wanted a flood abatement project, and instead of just putting in some dams and more canals or channelizing the river, they were going to take this whole area and sort of revegetate it and put the meander back into the stream, so that as water came down and when there was high water, this area would fill up with water and then slowly go down through the rest of the system. So they expected this would cost about $35 million. And they calculated what are the costs of these nuisance floods over a century, and every 10 years there's a nuisance flood. Not a lot of direct damage from the flood, it's just floods the local businesses in the streets, and it causes traffic problems, it causes a little bit of residential damage, because again, these are flood zones, so houses have been moved out of it. There's utilities and city costs. And just over 100 years of these 10-year nuisance floods, if you could avoid those floods, you would save yourself $15 million over 100 years. Then, and these are all normalized to the current dollars. Then the other thing is, what are the ecosystem services? So you say, well, here's thermal regulation of the stream, cleaner air, carbon storage, just like in the example up above of Costanza's work. Bird and fish habitat, recreation, ecosystem services, all of those add up to be $16 million. So if you put these two together, you get $31 million, the 16 plus the 15. It's pretty close to the 35. And what you end up with is a very functional, sustainable stream and set of ponds that will hold water, instead of some engineering solution that will just somehow dump the water under and pump it to get rid of floods. So this is an example of how City of Portland used the ecosystem assessment, assessment of ecosystem services to justify this larger project. Okay, now another thing that I want to mention is that the International Institute for Environment and Development looked at ecosystem services, and the reference is given below. But the problem was that in some areas, the water problems for poor people are exacerbated by the abuse of the ecosystem services. And what they did is not try to solve this, but set up a research agenda that would look at how you could manage these resources so it actually helped some of these poor rural areas that have water stress and low water availability, and look at the issues of governance, the variability and vulnerability of the water sources, the land use change in the whole area, hydrology, and then are there some market instruments that might help create this, provide a sustainable solution. All right, well, that's the end of this first part. In the next section, we're going to talk about smaller scale approaches to water pumping and purification, and then we're going to look at some of these indexes that illustrate these, illustrate how we would attach value and study this with accounting.